topic we're going to work on is this Master's theorem. So today in lecture I'll cover this Master's theorem, cover the two extra cases. I'll also talk about the substitution method, which you'll need for one of the problems on the homework. Then we'll get into algorithms. I'm going to talk about the first really non-trivial algorithm you probably haven't seen. It's for closest pair of points. That's a divide and conquer algorithm. We realize that there are many recurrences of this general form here, a times t of n over b. So you break the original problem into b parts, into parts of size n over b, and you break it into a of those parts, and then you spend a little bit of work, f of n, to put all those pieces together and come up with the solution. Last class we did one of these tree type of diagrams to get intuition for this summation. We basically wrote all of the work that would be involved in this summation here, and there are three types of behaviors that we'll commonly encounter. The first case is when the amount of work right here is actually quite small, and the amount of work at the bottom level of the recursion is where all of the work happens. In particular, this algorithm, the work is dominated by the fact that you're dividing the problem and recursing several times. Another case that can happen is essentially all of this is balanced. So f is balanced such that when you divide the problem into a factor of b and you make a of them, that roughly creates the same amount of work that you had in the previous layer. Quick sort or merge sort, the type of recursive algorithms that you've dealt with before, are in this particular case. And finally, the last case that could happen is the work is sort of front-loaded. This first step is the most work, and the rest of it gets progressively easier and easier. It all depends on how f of n relates to a and b. And when f of n is upper bounded by n to the log base b of a minus epsilon here, so this sort of upper bounded in a very strong way, then t of n is going to be theta of n to the log base b of a. In the case where all of the work is evenly balanced, then t of n is going to be n to the log base b of a times log of n. And finally, in this case, it's going to be f of n. Now there was one point that I glossed over in the last minutes of class, and there were some special conditions on f that I didn't want to get into last time, but I want to get into today. This Master's theorem works when f has this extra property right here, that there's some constant that's less than 1, such that c times f of n is an upper bound on a times f of n over b. It's kind of a weird condition, but in about a few slides we'll see exactly where that comes in. And we'll also go through examples which illustrate how you can test that condition. I want to recap very quickly how we went over the proof last time for case 1. And then I'm going to show you how simple it is to actually extend the argument to case 2 and 3. In case 1, we know that f of n is O of this particular value. If you look at that. Case 1, f of n is O of log base b of a minus epsilon. And so in particular, we know that there's some constant that upper bounds f of n this way. And so what we did last time is we simply wrote out what t of n would be upper bounded by applying that upper bound at each of these, right? So this is just going to be, if we write it out, we get that expression right there. And then we're going to apply 3 simplification rules, which I want you to remember. First, we recalled our classic summation formula, and then we had 3 facts. These little intermediate terms basically cancel out to b to the epsilon. This is something I want you to remember. A to the L is n to the log base b of a. And finally, b to the epsilon L is n to the epsilon there. Those 3 facts, we're basically able to simplify each of these terms to b to the epsilons, like that. And then we're able to simplify this summation down into this term right here. With that final fact, we're basically able to turn this into an n to the epsilon, and with slightly different constants, we're able to show this upper bound. And that, of course, implies that t of n is going to be upper bounded by n to the log base b of a. These two will cancel out, as we have on the next slide here. And I recall last class, many of you were asking, how do we do the lower bound? How do we do the lower bound? And I also thought in the homework, I basically asked you to do the lower bound, but I haven't really given you an example. Case 1, we showed the upper bound. Let's see how we can do the lower bound. Well, essentially, all we need to argue is that T of n is going to be greater than, we know that T of n is this summation, so we know that it actually has to be greater than this right here, a to the L. We can just erase all of these terms right here and say that, well, it has to be at least as big as this, and this right here, since it's one of these functions which we require to be positive, we know that it's going to be greater than 0. And so that's basically it, because what do we know about a to the L? It's n to the log base b of a, right? So this immediately gives us a lower bound that T of n is in omega of n to the log base b of a. So lower bounds can often be like this. You just forget about a bunch of terms and just include the right one that's big enough, and that's your lower bound. Go ahead, question? Yes. F of 1 just is going to be some constant. So f of n is going to be some constant that's positive. It's not negative. That's all I need, that is positive. Even if it's 0.00001, that will just be a constant that's hidden in this. So let me change this to be a of L times some constant. Case 2, when all of this work is roughly the same, when f is theta of n to the log base b of a, I'm going to show you why that's roughly exactly the same. Okay, so if we want to do an upper bound again, we know that c is bounded by this term. Notice that there's no epsilon anymore. And so when we write out all of these terms, we're going to get so if you write it out, notice that now all of these terms right here, the b in the denominator and the log base b to the a in the numerator, they're going to cancel out perfectly, right, with the a that's up here. So this is just going to be equal to c times n to the log base b of a times, this right here is just going to be a over a. This right here is going to be a squared over a squared. Everybody see why that works out? How many ones are there going to be? L minus 1, which is basically equal to log b of n, right? So this is my 3-line argument again. Question. Okay, remember L, it's the number of times we recurse. And every time we recur, we drop by a factor of b. This is just a typed up version of it. I'll post this one. To do the lower bound argument, because the assumption for this, right, was that f of n is in theta of n to the log base b of a, we know that f of n is actually greater. There's some constant c for which f of n is greater than this right here. And so we do that same step, and so we conclude it's exactly the same argument now, except the signs are greater than. When we don't have that little slight minus epsilon, then each of these terms become 1, and we get an extra log factor right here. But when this function is smaller, just by a little epsilon right there, then the contribution from this amount of work. The last thing I want to do is I want to explain why we need this special little rule right here for case 3. So notice case 3 says that f of n is omega of n to the log base b blah 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 plus epsilon, which means f of n is larger than something like this with some constant. Let's call it d. This is going to basically be f of n plus, now notice that this property right here, let me make myself a little bit of room, a of f of n over b is going to be upper bounded by this right here. That's exactly what this property means. But now if we take this term right here, a squared times f of n over b squared, we can write that as a times a. And now this part right here is going to be upper bounded by this same rule. So this is going to be upper bounded by a times c times I applied this rule once on this term in order to substitute this inner thing with this right here, and then twice I substitute it in order to get this right here. So this means that the second term is upper bounded by c squared times f of n. The third term is going to be upper bounded by, what do you think? C cubed, etc. So that is what's going to let us conclude that t of n is just upper bounded by this sum right here, which we can write as, and that is how we get an upper bound of just f of n, because c is a constant that's less than 1. In the homework, you had to do one of these summations for a sequence like this. When c is less than 1, you'll see that that summation is upper bounded by some constant. So where do we use this? Where do we use this step right here? So notice, let's say c was 2. Then we'll get a term of 2 to the L, which could be something like this, right? If c is larger than 1, this summation could be more than a constant, right? It could grow as n grows. When it's smaller than 1, each term gets smaller than the previous one. If it's larger than 1, these larger terms get larger than the previous ones. In the slides, I've typed out all of these equations so that what I want to basically leave you with here is this summary, and then we're going to go through a few examples. That's what that handout is today. We have 4 examples. We'll do 2 really quickly, and then we'll do 2 in pairs. So how does this work? We identify A, we identify B, and we identify f of n. Well, we conclude that f of n is equal to theta n squared, and n to the log base 2 of 8 is equal to n cubed. And so in particular, since theta n squared is upper bounded by n to the 3 minus epsilon for, let's say, epsilon equals 0.1, it doesn't matter. By case 1, t of n is n cubed. Basic steps: identifying f, identifying a and b, right? This was a, this was b, and then picking which rule right here. Once again here, this is a tricky one because f of n is what? Theta 1, right? And a is equal to 1 and b is equal to 17 over 14, right? Because it's n over b. You have to rewrite this fraction. And so n to the log base 17 of 14 of 1, that's going to be n to the 0, right? Which is upper bounded by 1. So in this case, does case 1 apply? Okay. Case 2. Yes. So t of n is basically theta of, it's theta of n to the 0 times log n, which happens to be that. When you write something like this, the log base does not matter because there can be an extra constant in this theta notation. So you can assume that logarithms in big O notation are always base 2. Now, the next 3 examples I want you to do. Pair up, and I'm going to give you 2 minutes, and I want you to solve these things. Here we go, a and b. F of n is n cubed, and we should have essentially, so f of n cubed, n to the log base 2 of 2 is n right here. So this is theta of n to the 1, right? And so case 1 doesn't apply, case 2 doesn't apply. Case 3, f of n certainly meets the definition that it's in omega of n to the 1 plus epsilon, right here, for epsilon like 0.1. So now what about this question about whether there exists a constant c? Well, so let's test. So we know that, is there a c such that 2 times f of n over 2 is less than c times f of n? if we just plug this into the definition of f, we get that if c is equal to 1/3, the condition holds. So this implies that t of n is going to be in theta of n cubed. Next example, which case and what's the answer? Case 2. And the answer? Great. Which case? Case 1, and t of n is equal to 2 of 7. Now, the reason we're going to do this example, Strasson's algorithm for multiplying matrices, right? What's matrix? Matrix multiplication, right? N by n matrix. It normally takes n cubed operations if you implement it in the simple, straightforward way. Strasson's algorithm achieves this complexity. The last thing I want to do is talk about the substitution method for solving special kinds of recurrence. And your homework has one example of this. Let's take this recurrence right here. Let's do it our old-fashioned way. First, what we're going to do is make a tree. So we know that our function will be evaluated on n, and then it'll make 2 recursive calls of size n to the 1/2. And at this level, it will incur log n work. And over here, it's going to do half of log n work. And notice this is natural log, but it doesn't really matter whether it's natural log or log base 2. At the next level, there'll be instances of size n over 1/4. And the work would be 1/4 of log n. Okay? And this is going to continue like before until we get to some sort of constant here. And so now the question is, if we assemble how much work is involved here, here we had log n, here we had also log n, here we had log n as well. At this level, we'll also have log n. The question is, how many levels? So how many levels do we need? Well, we know we start with n, then we go to n to the 1/2, to the 1/4, to the 1/8. What we're looking for, the number of levels is going to be such that n to the 1 over 2 to the L is going to equal some constant. 1 isn't a good example, but 2 would work in this situation to give you the right intuition. How many times do you have to take a square root until you get a constant? And now we can solve this using my favorite method by hitting the logarithm. And so if we take logarithms on both ends here, we're going to get some constant. And so if we do it again, I change from I to L. So the number of logarithms you take is log n. And so this gives us a good guess that t of n is going to be upper bounded by log n times log n. I'm going to show you in the very next slide a simpler way to do this. The first step is I'm going to consider what happens. I'm going to have 2 ideas here, just 2. I'm going to consider what happens when we set 2 of m, so in other words, m is equal to log base n. So t of 2 to the m is equal to 2 times t of m over 2 plus, do you agree that if we just substitute 2 to the m here, we get that? If we substitute square root of 2 to the m is just 2 to the m over 2, right? And log of 2 to the m is m. It's going to be some constant times m, but we can just kind of forget it. Now the second idea I'm going to do is I'm going to introduce another recurrence. S of m is going to equal. And so if I just substitute now and rewrite my recurrence, S of m is going to be 2 times S of m over 2 plus c times m again. Now, what can I use? Master's theorem, case 2. So we know that S of m is going to be theta of m times log m. And so now we just substitute back. We know that t of n is going to be theta of log n times log n. So that's the substitution method. It makes use of this Master's theorem, which does a lot of work for us. Where does this c come from? Well, technically this is natural logarithm, and we're substituting with, this would be the natural logarithm of 2 to the m, so it'd be some constant times m. Question in the back. Good question. Let's figure it out from first principles. So let's say you had log of log base 10 of n. That's your question, right? So that's going to be equal to log of, let's put some constant here, d times log base 2 of n. So this is going to be log of d, if the product of logs is a summation, right? So the base of the inner log came out the first time, and now it's a product, this times that, okay? And the log of products, you can split them and sum them, right? So then this is just an additive constant. So it doesn't really affect the growth, the asymptotic. Now I'm really excited about this, the algorithm we're about to do. Before we can get there, I have to give you some intuition, right? We have a big problem, we slice it into parts, we solve those parts, and we glue them back together to come up with the solution for the big problem. That is divide and conquer. Okay, you've seen merge sort. You've already seen caret suba. We're going to see a few examples. So this is closest pair. We're going to see an arbitrage example. We're going to see the FFT example, fast Fourier transform. So these are some very, very cool algorithms that we're going to talk about here that use divide and conquer, that are not trivial ones. But you know what? They all start with the same basic formula. I know that you have seen merge sort, and so I want to go over this very quickly, but I want you to pay attention to the formula, to the structure of how this works. Merge sort, here is the algorithm, right? You recursively sort the halves of the list and then merge them together. You divide the first list into 2, you divide it into another list of 2, you finally come to single elements, okay? And then you recurse back. Now you merge 5 and 2 to get this list, you merge 4 and 7, you merge 1 and 3 and 2 and 6, and now you merge the blue into the orange, okay? Merge, remember, you just have pointers at the front of each of these lists and you scoot those pointers along, always picking the smallest value first. Divide the problem in half, solve them, and put them back together. The only twist that we're going to add here is that when we divide them in 2 and solve them, we might produce extra information, or we might have a very clever way of gluing these solutions back together. That's where the algorithmic complexity comes in, but this is the basic structure for this. Okay? Now, to analyze this, of course, we see that these two steps, again, are t of n over 2. This is order 1, and this is order n. And so, by the Master's theorem, question. The merge operation, if you remember, to merge two lists of size n over 2, you basically keep a pointer over here and a pointer over here. Okay? Let's merge these two rows right here. You and you, which one is younger? Doesn't matter. Let's assume you're younger, okay? So then he's the first in the list. Then I have a pointer between you and you. Which one's younger? He's younger. Then I put him in the list, right? And I move my pointers. You see? I just kind of scoot them around like this. Okay? And I get a merged list. And the amount of work I do is proportional to the number of times I have to move my pointer. I only move my pointer exactly n steps, right? Because I never go this way. I only go this way. And so the number of pointer moves over here is n over 2, and the number of pointer moves over here is n over 2. Does that make sense? Well, these are sorted, right? At this point, when I'm running this merge right here, these two lists are sorted. So all I'm doing is merging them. I'm comparing 2 with 1, picking the smaller one, and moving the pointer over. Yes, and I've already counted that work there. So in particular, when I give you the algorithm in these 3 lines right here, you don't have to worry about, you're getting confused about counting work for a previous layer in this layer. That work is going to be accounted for in this term right here. That is the amount of work that it took to sort that list, which included the merge step in that bottom layer. It's easy to get confused about where to count for work. That's why the tree method doesn't work so well. That's why it's better to just write the running time in this very simple way. Here is a very, very cool problem. Very cool problem. It's the closest pair of points problem. And here's how it works. You have n points in the plane, right? These could be it could be like stores, it could be satellites that are in space, and you want to make sure that these satellites don't hit each other. The problem is, find the closest pair of points given these n sets of points. Very classic problem. If you're in a video game and so forth and you are moving some character, you need to find what is the closest piece of geometry to this, because I need to make sure that it's not going through a wall or whatnot. Problem comes up all the time. We're going to solve a simple version of it. You're given these n points, and you want to find the pair that's the closest. The brute force solution, take this guy right here and compute distances to all of his buddies. Then that's step 1. Step 2, take this person and compute the distances to all of her buddies that haven't already been computed. What's the problem with the brute force solution? If we write it as a recurrence, it's going to be something like this, right? I first compute the closest point that's closest to this point. Okay, that takes order n time because I look at all of my neighbors. And then I look at all of the points except for this one and try to find its closest pair and compare the two. And eventually I'll get to the pair that is the closest, and that'll be that. That takes order n squared. And that's not a good algorithm. We're going to do better. Just like with sorting, crappy sorting is n squared, good sorting is n log n. We're going to do n log n with this. But on face, does this problem look anything like sorting? You're not arranging the points in any particular order. You're not comparing them. First of all, it's two-dimensional. It's not just comparison of these points, right? And you're not sorting them. You just want to find this closest pair. On face, I'm going to say this problem doesn't look like sorting, but it turns out it has the same structure of a solution. We're going to split it into 2, do stuff, and then put our answers back together. So how are we going to do this? As I mentioned, the first step is to split into 2. So we can divide the set of endpoints into a left half and a right half. And we might as well recursively find the closest pair in the left and the closest pair in the right. I think it might be this one maybe, I don't know. Recursively solve the problem on the left and the right, and we get a delta. I think this delta is going to be smaller than this delta prime, okay? So we get the 2 answers and we compare them. And so now we know that our answer has to be either this pair right here or another pair that is closer than delta. Where can this other pair be? Yes, we could have a Romeo over here and a Juliet over here. Soft! What light through yonder window passes? So what we're going to look for, we've recursively broken into 2 parts, solved the left and solved the right, and now what we have to do is just check if there are any Romeo and Juliet situations that are smaller than delta. We know that we've already recursively found the closest pair on the left. We know that no pair on this side can be smaller than delta. Similarly, no pair on this side can be smaller than delta because it was delta prime, right? So the only way there can be a pair that's smaller than delta, the only way this pair loses the race right here is if there is a point on this side and a point on that side, because we didn't compare them. So all we now have to do is look for Romeo and Juliet situations. Now maybe the point you're saying is, well, this guy could be a Romeo and that guy could be a Romeo, and so you're going to have to check all n squared with all n squared. Is that your point? So your essential question is, how do we look for Romeo and Juliets without spending n squared time? The first observation is Romeo and Juliets are only going to be within delta of this middle line. They're not going to be over here and over there because then they would be too far, they would be farther than delta. So we only have to look in this mohawk right here. But unfortunately, that's really not enough because it could be the situation, here's an example right here, where all of our input points, here's the line right here when you split in the left in half, all of our input happens to be in the mohawk. All n points are in the mohawk. We are close. We know that the structure is divide, divide, find something in the mohawk. And now the question is, it could be the situation we have a bad mohawk, all of our points in there. We can't just check all pairs that are in the mohawk. This is the put it together. This is like the merge in merge sort. The putting it together is often the most tricky part of these type of things. And here you need an algorithmic insight. Here is the insight that this algorithm uses. Let's take our mohawk and let's divide it up into little cubbies. These cubbies are going to be delta over 2 by delta over 2. Here's a picture of this. So what I did to divide my mohawk into cubbies, I found the point that is the lowest, the lowest point on the y-axis. I started right there, and then from my middle line, I basically drew little boxes that are delta over 2 by delta over 2. Those are my cubbies. And here is the point. Why did we draw into cubbies? What we're going to say is that cubbies are very lonely. If you draw a box that's delta 2 by delta 2, okay, at most 1 point per cubby. Why is that? Because let's say that there was a point at the extreme spot right here, at the extreme left corner. And the farthest a point could get would be this extreme right corner. What is this distance right here? Yes, it's going to be square root of 2 over 2 times delta, right? Good old Pythagorean. This happens to be less than delta, right? Because square root of 2 over 2 is less than 1. So therefore, this can't happen. We already know that delta is the smallest distance between any points on the left side or any points on the right side. These cubbies are all either on the left or on the right. And so therefore, each of these cubbies have to be single point or 0 point. That's our first insight. Cubbies are lonely. How do we use this fact? Let's imagine this is our little Romeo right over here. How far do we have to look for Romeo's Juliet? We know that there's one guy here, at most one guy there, at most one guy there, one guy there, one guy, one, etc. If we put a circle of radius delta right over here, this gives us a nice bound on the number of cubbies that Romeo needs to look at. When he opens up Tinder, there are only going to be 15 possibilities for his match. If we put the circle right there, that's how many boxes. If we put a circle at the other corner and we put another circle at that corner, that's where Juliet could be. If life were so simple, if you knew that your Juliet was just 15 boxes away from you, life would be great. And that's how it is with the Mohawk algorithm. Okay, so how does this algorithm actually go? Here's another example. If the point is right there, then again, there are a certain number of things. The point is count the number of cubbies that are covered by this. I'm going to tell you right now it's 15. We'll do a better counting in the last few minutes of the next class. You start at the lowest point and you look at these boxes, the 15 cubbies where your Juliet could be. If you find a Juliet on the other side there that's smaller than delta, keep that distance and keep that pair. Next, go to the next point along y in y order. So we're going to walk up these points in y sorted order and look at its possible boxes, and so forth. So we look at all the points in our Mohawk. Fact is, we only have to check 15 of its nearest points. 15 of its, in sorted y order, we only have to look at the next 15 points in the list and check if there's a Juliet in that side. I don't care, we're going to make that number from 15 to 7, etc. It's going to be constant, right? It's constant. That's the point. For every point in the Mohawk, we only have a constant number of checks for its Juliet. That makes that last step of checking the Mohawk linear time. And that gives us a recurrence that looks like this, which gives us n log n.